Hello everyone, this is Juan Fraire and this is another video for the Managed Kubernetes for Machine Learning series we are developing at Cloud & Hits. This is a series of videos where we want to explain how can we develop easily machine learning applications, pack them into Kubernetes containers and deploy them into our infrastructure at Cloud & Hits. Today, we're going to see an example on how to create a very simple machine learning application using Keras, which under the hood is based on TensorFlow. And we're going to be coding in Python using Visual Studio Code. In particular, in this example, we're going to be using a linear regression, which is likely the simplest model that we can use for machine learning application. And this is a good means to understand the overall workflow that we will need to follow and that is typically followed in machine learning applications. A linear regression is a technique where we want to train or we want to develop or we want to parameterize a model that can follow a given set of data or can model a given set of data using just linear variables, linear parameters. So we're going to first load our dataset. We're going to get some intuition on how the dataset looks like. We're going to plot it. We're going to create a model. We're going to define how the model is structured. We're going to train this model. We're going to inspect how this model looks like, and we're going to use it to make some predictions. So the very first step that we want to follow is getting our dataset and loading our dataset. This is the data that we're going to use to train our model. So this is the very first part that we have defined here. So for this, we're going to import pandas. This is a Python library for handling data. And we're going to use it to load our housing.data dataset. This dataset is a dataset composed of information of housing in Boston. This dataset is publicly available for download from this webpage. And this is composed basically from two main files. One is housing.data and the other one is housing.names. The data is naturally on the .data file, and the .names files actually include some information on how this data is structured. Let's see what this file has inside. So this is housing.data that contains most of the numbers and data that we're going to be using, or at least some of them we're going to be using. And the .names file actually includes information on where the dataset is originated from. I will leave this to you to take a look at it. But we're going to be taking a look especially to a few variables. So this is a dataset that has information about housing in Boston. And we're going to try to study and to model two aspects of these datasets. One of them is the age of the house. This is column number 7 from housing.data. And we're going to understand how this parameter is actually related to the price of the house. And this price is actually modeled in column number 14. This is the median value of the house expressed in thousands of dollars. So we're going to be exploring column number 7 and column number 14 from this dataset. So going back to our Python script, we're going to be using pandas to read this information. From this file, we're going to be taking columns 6 and 13. This is because the counting in arrays starts from 0. So these are column 7 and column 14 of the housing.data set. And since the data set is separated by spaces, we're going to be using some parameters to indicate this. And since the file has no header, we are indicating that it has no header. And we're going to be using the names argument here to show that actually these headers of these columns that we're loading actually are the age of the housing and the median value of the housing. So let's uncomment this print line here and just run the script to see how this dataset looks like. So I'm going to broaden here my terminal, and this is the printout of the dataset. So we have the age column here, we have the median value column here, and we have the number of elements, which is a little bit higher than 500 lines of data from this dataset. So this is the data that we're going to use to train our model. But this is very important to get some insight on how this data looks like. So I typically suggest that if possible, we should try to plot this data and understand how it looks like, so we can get some intuition on what is the model that we're trying to develop here. So to this end, I'm going to show how this looks like using matplotlib. Matplotlib is a library for plotting data in Python. And what we're going to do is just basically from the same data element from the pandas that we have just created, I'm going to plot a scatter plot using the age as x-axis and the median value as y-axis. I'm just going to run this right now to see how this plot looks like. So this is the plot, scatter plot of the data that we're using, right? So we have the age of the housing, and we have the median value expressed in thousands of dollars. And these are the different data points that we're taking from these data sets. So what we want to do now is to create a model that can somehow represent this data and allows us to make some predictions on this data, so that we can input some age and understand what is the median value that age house of that age can actually have in real. So we're going to do the next step is to create a Keras model for this. We're going to be using a sequential model. Sequential model is one of the most used model in Keras and basically represents a linear stack of neural network layers. And for doing this, we're going to import Keras model from, we're going to import sequential from Keras model. And just in this line 22 here, we are basically creating the object model. We're going to be configuring the layers that this model has in the next step. So we're going to be using a type of layer which is called dense layer. So this is a very popular type of layers also in neural networks, where every neuron in the layer is fully connected. This is why the name dense comes into play. So this means that every neuron in this layer are connected to the input and the output layer. The input layer that we're going to be using in our model is naturally the age of the housing that we're using. And the output layer, which is the result, this is basically what we want to predict, is going to be also the median value of the model. And naturally, these are unidimensional values, right? So age is a single number and median value is a single number. So we're working basically on a single dimension input data structure and a single dimension output data structure. So this is in favor of what we mentioned at the beginning. So this is a very simple model that we can use, so we can understand the overall data flow of working with machine learning applications. So in the next lines, what we're basically doing is declaring these dimensions, and we are basically adding to the model one of these layers with the configuration of the dimension that we have just mentioned. So since sequential is basically a stack of layers, we can use this add function here from Keras in order to add a new dense layer, in this case, where it has an output dimension of 1 and an input dimension of 1 as well. Another parameter that we need to define in layer is the activation parameter. In neural networks, activation refers to the function that operates inside each neuron in the neural network. And linear activation is one of the simplest and likely one of the, let's say, more compute efficient. Naturally is a linear function and is actually favor or linear regression model that we're going to use. We're going to see also other activation types in future videos as well. But for the sake of this tutorial, it's enough to understand that the linear activation is a relation between the input parameter of the neuron and the output parameter of the neuron, which is naturally linear as we are defining at this point. So to get some intuition of what's happening under the hood, we are going to uncomment this line here, and we're going to plot a summary of the model that we're running. So I'm just going to run this point of the script until this point now. So we can see actually here that now we are using the TensorFlow backend. So this means that we are actually using and creating this model. And let's zoom out a little bit here to see what's happening. So this is the output of the summary of the models. So what we're getting from Keras at this point is that we're using a single dense layer. We have a single dimension in this case, and that it has two parameters that we will need to train and to optimize. So moving on with the program, we have our model created, we have our layers defined, and now what we need to do is to train and to understand what is the value of these two parameters that we're going to use in our model. And this is to get understanding and making a guess on what these parameters are is what's called training the model in machine learning terminology. So training a model means that based on the data set that we have, we need to run some algorithm to determine which are the two parameters that actually fit best to model the data that we have. One of the most common algorithms to make this happen is known as stochastic gradient descent algorithm. And this is just an algorithm that, based on the data set, tries to get the derivative of the data or the slope of the data that we're using in such a way that they can approximate the minimum value of a loss function. A loss function that is, in this case, is going to be measured by a mean square error value, right? Where the error value is the difference between what the model actually is predicting and what the real data says that it should look like. So what we want to do is to minimize this difference. We want to make this difference as small as possible. And this is why we are actually running an optimization approach using the gradient descent algorithm to make this loss value as low as possible. If we make this loss as low as possible, then we are actually getting the parameters that actually fit the data the best. Now, why this is called stochastic? The reason for calling it stochastic is that the algorithm doesn't necessarily run over the whole data set. It runs over what is a batch of the data set, which is a small portion of the data set. So we're going to see in the next step why are we saying that this is a batch execution. But for the moment, we are only interested in knowing that we're using a loss function for measuring this mean square error. We're going to use this SGD, standing for stochastic gradient descent algorithm. And one of the parameters that we're using for defining this SGD is the learning rate. And the learning rate in the optimizer stands for which is the speed at which during the training the model forgets previous values. To say some in another way, the learning rate is how fast you're actually approaching, or you try to approach, the minimum value in the plot. And this is where you don't need to be too aggressive on this point, because if you are too aggressive on the learning rate, then you are, while you're surfing the data, while you're browsing the data, you are likely to overshoot the minimum value and to go over the minimum value and skip it. So you need to be sure and play a little bit around so that you have a learning rate that actually fits the data that you have. So it's a parameter that for our dataset, this value that we have here is enough, but this is a value that actually defines and actually governs how your training is going to be in your machine learning application. So let's move on with the next step, which is to train the model. So to train the model, we're going to use the fit function provided by Keras. So from the same model that we have created, we're going to use this function to provide, on the first place, the data set of the age of the housing that we have already loaded. We're going to provide the y variable, the value that we want to use for prediction. This is the median price of the housing. And we're going to add a few other parameters. One of them is the batch size. This is what we mentioned previously. So batch size is for how many, what's the size of the data sets that we're going to use for running on each iteration. And this is where the stochastic word for the SGD algorithm comes into place. This is we're going to take batches of 20 sets of 20 points of our data set and run through several iterations and for going over and browsing the whole data set. When we browse a whole data set, we say that we have completed an epoch. An epoch is thus a set of back and forward passes over the training data in batch size of 20 in this case. So this is one epoch. And then we are saying that the fit of the algorithm should have 3,000 epochs. This means that we're going to go over back and forth 3,000 times. And in this approach, what we're actually doing is basically understanding and approximating the parameters by minimizing the last function that we have already mentioned. So to be clear about this, if we currently have 500 data points in our data set and our batch size is of size 20, then this means that we're going to be running 25 iterations per epoch. and then we are going to be running 3,000 epochs, and this is the whole training process that we're going to follow. And then we have a verbose parameter that show us whether if the model training should expose data in the console as it trains. So now we're going to run this and see how it looks like. This is the output of the console while the model trains. Here you can see that basically the K8s is showing us how much time is taken on each step, and this is in the order of a few hundreds of microseconds. We can also see which is the loss value of the loss function, and as you can see throughout the iteration, this number is trying to go down, and this is actually show how the gradient algorithm is trying to explore the data sets and the different parameters so that this number goes lower, and meaning that our linear model is going to fit the data better. And we also have the epochs and the number of epochs on the order, in this case, of 500 in the out of 33,000. So I'm going to speed this up a little bit so we can go to the next step. So now our training has finished, and we can see that we have run 3,000 epochs, and we ran for each epoch, we went through the full dataset of 506 points, and the loss function in the last run was of 83, taking around 144 microseconds. So at this point, the model is completed. I'm just going to go over this. I'm going to come back to this later. And we have this instruction here that actually was calling from our model, getting all layers. In this case, we have a single layer, so we're actually having a single parameter 0 here, getting the first layer that we have, first and unique. And we're basically getting the weight of this layer that we have in our model. And we're just plotting these weights. And these are actually printed out here in the console. And these are the two parameters that actually define our machine learning model at this moment. This is the weight value. This is the first variable you have here that's got from the layer. And this is the bias values that we have here. We're going to see, in order to understand what these numbers means, we need to plot the data and we need to plot the model. This is what we're going to do right now. But before doing this, we want to run the model again. We want to run this program again, and we don't want to train it again because we already know what are these variables already looks like. So instead of running everything again just to plot the variable and in order to avoid to run the training once more, we're going to comment this out, and we're going to see that there is an alternative step. So instead of training the model as we have just did, we're going to directly provide K8s the weight and the bias parameter we have just calculated. So I have this commented here, so I'm just going to uncomment this and check what we're doing here. So in this alternative step, we're having importing NumPy. This is a numeric library for Python, and we're just manually populating. In this case, I'm doing this manually, but in a real application, you will likely train your model and you will likely save these numbers in a file and parsing this in your Python script or your main program. And we're just basically doing this manually here to speed up the things. But with this, we just basically get these two variables, and we can force the model and specify K8s to configure this weight and this bias value directly to the model instead of training it, instead of going through this whole computationally expensive process. So I'm going to do this right now. So we can see the model is here. So we still have two parameters and so on. So everything is okay. So now I'm going to remove this summary printing here. I'm going to go to the plotting area. We want to plot this data, and I also want to plot the model to understand how this looks like. So this is where we're sitting right now. So after setting the weight and the bias, I'm just carrying the model once more to get me the weight and the bias again, just to be sure that we're having the right values. And now I'm going to be plotting two things. We're going to be using two subplots here in Matplotlib. So in the first one, we want to plot the history of the training data that we have used. And this is going to be a plot that will take the mean square error parameter from the training history. And I'm going to plot this again, the epoch, so we can see how this error actually changed and evolved through the epochs while we were training our model. And on the second plot, we're going to be using a scatter plot to plot the age and the median value of the housings of the dataset that we're doing. So this is the same scatter plot that we did at the very beginning. But we're going to add this plot with a linear plot, a plot of a line that actually, for each age value that we have in our dataset, we're going to use it as a prediction and feed the model with this age value so that the model can actually predict what's happening based on the parameters that we have configured. And we're going to see this as a line in the plotting. And we just have some other functions here, like a y label and x label, just to set in the plot properties. So and then what I'm going to do is just to show these plots, print the weight and the values just to be sure that we're having the right thing here, and then I'm going to terminate the program. I'm going to run this right now. Alright, and this is the result of the plot that we have just mentioned. Let me make this a little bit bigger. So what are we seeing here? Let's go over this data a little bit. So on the one hand, we mentioned that we were plotting the median square error value that was recorded throughout the epochs during the training phase. We had 3,000 epochs. So for each epoch, we have how this mean square error value went down from starting from around 225, 250, and it went down to something a little bit higher than 75 in this case. And this is what happened during the training process. And this is the grading algorithm that is continuously trying to find the minimum of the loss function. And we can see that this is a stochastic and this is a best effort algorithm, because in many places we see some spikes, which means that sometimes this algorithm is actually jumping from one point to the other and going further away from the minimal data that we were looking for. So this is why this is stochastic, and this is why this needs a lot of computing power to be done, because this is basically a trial and error with some smart intelligence basically pushing forward the looking strategy here. And on the right hand side, we have the same scatter plot of the data that we have for the housing values. Again, the age of the housing on the x-axis and the median value in thousands of dollars on the y-axis. But now we also have the linear model that we have in here. This is red line here corresponds to the prediction of the model for each age value that we are providing as input of the model. And we can see actually that it follows quite close the general trend of the pricing of the house throughout its age. Naturally, the older the house, therefore the lower the price that it has. And it is interesting to note at this point that if we basically hand over with the mouse using Matplotlib here, we see that on this part of the window here, we see the x and y values, and we can see that actually the y value is 27, and we can actually see that this 27 drops down to something around 18 at the end. And we can see that actually the value of the slope of this curve, of this line, actually is 0.1. And the constant value of the linear part actually is 27. And these actually are the two parameters that we need in order to plot this line using a linear equation, a traditional linear equation. And it's interesting to see that actually the neuron of the dense layer that we have configured for a model actually needs two parameters, and these two parameters are the two parameters that are used for using a linear equation system. So this is why this example is one of the simplest examples of machine learning that we can use, because we're using neural networks, but in the end we're using a very simple mathematical process to derive a linear equation that can fit and somehow follow the model of data that we're currently using. And with this, we close this tutorial. But the message is the following one. This was a very simple model. It was a linear model with only 2 parameters. But what is important to notice is that the principle of machine learning remains the same for any more complex model or more complex data set. So instead of having 2 parameters in our neural networks, we can have hundreds of them, right? And instead of having a unidimensional data set as input and a unidimensional data structure for output, we can have many dimensions of input as output, but the principle remains the same. This is the same data flow, the same workflow that you need to follow in order to deploy your machine learning application. Also, the training phase, it's important to highlight that this requires a lot of computing power, and this is something that actually is what the Managed Mesh Kubernetes project actually brings to the public, which is using infrastructure of computing power from Cloud and Heat in order to train your model instead of having you to provide the same computing power that you need to have this done. So this is why this video is part of a series of videos, and we're going to, in the next videos, we're going to go into more complex models, more complex studies of neural networks, and we're going to explain as well what is needed in order to deploy these applications into Kubernetes infrastructure such that you can actually leverage the computing power of Cloud and Heat infrastructure for training your own models. So thank you for listening and stay tuned.